Today we discuss the row space, column space and null space of a given vector space, which are important spaces associated with matrices. The work here will give us a deeper understanding of the relationships between the solutions of a linear system and properties of its coefficient matrix. Suppose A equal to Aij m by be an m by n matrix, then the vectors formed by the rows, that is the first row, let me call it as R1. R1 is the vector A11, A12, etc. A1n. R2 equal to A21, A22, etc. A2n, etc. etc. Rm equal to AM1, AM2, etc. Amn. Note that each of these vectors has m components and are in Rn. So these vectors are known as the row vectors of A. Note that the row vectors are formed by the rows of the given space, the given matrix. Similarly, we define the column vectors, and obviously they are in Rm because each of these vectors are in has m components. So we have the following definition. Let A be an m by n matrix. The space spanned by the row vectors of A is called the row space of A, and it is denoted by row of A. Obviously, it is a subspace of Rn. So the subspace of Rn, which is formed by the linear combinations of all the rows of A, is the row space of A. That is the term spanned by means. Similarly, we define the column space of A, and obviously it is a subspace of Rm. And the third definition is the solution space of the homogeneous system Ax equal to 0 is the null space of A, comma denoted by null of A is a subspace of Rn. So the collection of all x satisfying Ax equal to 0 is in the null space. Okay, all these are subspaces of either Rn or Rm. So the first theorem: a system of linear equations Ax equal to b is consistent if and only if b is in the column space of A. So we have to prove that if Ax equal to b is consistent, means is solvable, then b is in the column space of A, or b is spanned by the columns of A. And if b is in the column space of A, we have to prove Ax equal to b is solvable. So consider the linear system Ax equal to b, where A is an m by n matrix, x is the column vector, x1, x2, etc. xn. Suppose c1, etc. cn are the columns of A. Then Ax will be equal to x1 c1 into x2 c2 plus x1 c1 plus x2 c2 plus etc. plus xn cn, and therefore Ax equal to b is equivalent to x1 c1 plus x2 c2 plus etc. plus xn cn equal to b. And it implies Ax equal to b, which is a linear system of m equations in n unknowns, is consistent if and only if b is expressible as a linear combination of the column vectors of A. So if Ax equal to b is solvable, then this happens, and vice versa. So that means b is in the column space of A, if and only if b is in the column space of A. That is the first theorem. So in order to prove that the system is consistent, it is enough to prove that b is in the column space of A, or b is a linear combination of the columns of A. Second theorem: suppose x0 is a solution of Ax equal to b. Okay, we call this as a particular solution of the system. An x0 satisfying x equal to b is a particular solution. And suppose S is equal to v1, v2, etc. vk is a basis for the null space of A. Okay, that means these satisfy. So basis for the null space of A means a v1 equal to 0, a v2, etc. a vk equal to 0. And these are linearly independent and spans the null space. Then every solution of Ax equal to b can be expressed in the form x is equal to x0, which is a particular solution, plus c1 v1 plus etc. plus ck vk. Conversely, for all choices of c1, c2, etc. ck, the linear combination x0 plus c1 v1 plus etc. plus ck vk is a solution of Ax equal to b. And we don't have the proof in the syllabus. So we define x0 as a particular solution and the vector c1 v1 plus etc plus ck vk is known as a general solution of the system Ax equal to 0. Okay, so using this, so we can write x is equal to the statement is like this, then every solution of Ax equal to b can be expressed in the form x is equal to x naught plus c1 v1 plus etc plus ck vk. So this x is any solution. That means this particular x is a general solution of Ax equal to b, which is nothing but the sum of the particular solution of Ax equal to b and the general solution of Ax equal to 0. So we have the theorem in the as follows: the general solution of a consistent system Ax equal to b can be expressed as the sum of a particular solution and the general solution of the corresponding homogeneous system. Let us discuss certain examples. Given the matrix A and a column vector b, determine whether b is in the column space of A, and if so, express b as a linear combination of the column vectors of A. So by the first theorem, this is possible if and only if Ax equal to b is consistent. That means b is in the column space of A if and only if Ax equal to b is consistent. So it is enough to verify whether Ax equal to b is consistent or not using the methods we have already studied. So here A is given as the by row wise 1 1 2 1 0 1 2 1 3, and b is the column vector minus 1 0 2. So let us solve the system Ax equal to b, where A is given, b is given, and x is the column vector x y z. So we consider the augmented matrix and row reduce it. So you will get by reducing it, we have the matrix 1 0 1 0 0 1 1 minus 1 0 0 0 1. Okay, so corresponding to A, the row reduced echelon form is 0 1 0 1 0 1 0 1 1 0 0 0. So correspondingly the matrix equation will be equivalent to x plus z equal to 0, y plus z equal to minus 1, and 0x plus 0y plus 0z equal to 1. The third equation means that the given system is not solvable, and hence Ax is equal to b is inconsistent, and therefore b is not in the column space of A. So we cannot write b as a linear combination of the column vectors of A. Now another example, given A and given B. So let us consider the augmented matrix. So by row reduction, we have obtained x equal to 1, y equal to 2, and z equal to 3. So therefore the system is, that means the homogeneous, the linear system of equations Ax equal to b is consistent, and therefore by the first theorem, Ax equal to b is consistent if and only if b is in the column space of A. Therefore b is in the column space, and hence it can be expressed as a linear combination of the column vectors of A. So the b is from the solution Ax equal to b, we have b is equal to 6 to 1. So if you write this as some A into, say, the first row, column vector is 1 1 2 plus b into 1 minus 1 1 plus c into 1 1 minus 1. So you get a system of another 3 equations. Or in this particular example, just by inspection we can get 6 to 1 equal to 1 into 1 1 2 plus 2 into 1 minus 1 1 plus 3 into 1 1 minus 1. So always we can write the coefficients as the solution itself. So x equal to 1 is the coefficient of the first row, first column vector. Y equal to 2, y is the coefficient of the second column vector, and z is the coefficient of the third column vector. Another example, suppose that x1 equal to 3, x2 equal to 0, x3 equal to minus 1, and x4 equal to 5 is a solution of a non-homogeneous system Ax equal to b, and that the solution set of the homogeneous system Ax equal to b is given by the formula x1 equal to 5r minus 2s, x2 equal to s, x3 is equal to s plus t, and x4 equal to t. So find a column vector form of the general solution of Ax equal to b 0. So this is the general solution, x1, x2, x3, x4 given, and find a column vector form of the general solution of Ax equal to b. So given that the general solution of Ax equal to 0 is x1 equal to 5r minus 2s, x2 equal to s, x3 is equal to s plus t, and x4 is equal to t. So this can be expressed as r into 5 0 0 0 plus s into minus 2 1 1 0 and plus t into 0 0 1 1. So we have expressed the solution, general solution of ax equal to 0 as or in vector form. Then the general solution of ax equal to b by theorem 2 is the sum of the particular solution of ax equal to b, which is given as x1 equal to 3, x2 equal to 0, x3 equal to minus 1, and x4 equal to 5, and the general solution of ax equal to b, which is 5r minus 2s, s comma s plus t and t. So taking the sum of these two, we expressed the general solution of ax equal to b as or in column vector form. Now let us see how to find out the basis for the row space and the null spaces. Okay, we know that elementary row operations on the augmented matrix where b is augmented to a of a linear system ax equal to b does not change the solution of the system. We already know that the solution of the system is not changed by elementary row operations. The same is true when b equal to 0 also. But note that when b equal to 0, the elementary row operations does not affect b, because it's always any elementary row operations will not change 0. Okay, so the solution of ax equal to 0 is unaffected by performing elementary row operations on a itself. So instead of performing these elementary row operations on the augmented matrix for ax equal to 0, it is enough to perform the elementary row operations on A itself. So we have the following theorems based on these observations. Theorem 3, elementary row operations do not change the null space of a matrix. So the null space is given by Ax equal to 0. The solution set of Ax equal to 0 is in the null space. Okay, so elementary row operations do not change the null space of a matrix, and elementary row operations do not change the row space of a matrix. The row space of a matrix is also not changed by elementary row operations. These are the two theorems whose proof is not required. So based on this, we will discuss certain problems. Find basis for the null space of a row space of a given a equal to 1 4 5 6 9 3 minus 2 1 4 minus 1 minus 1 0 minus 1 minus 2 minus 1 2 3 5 7 8. Okay, 4 by 5 matrix. So the null space is given by the solution space of Ax equal to 0. So, and we know that by theorem 3, elementary row operations do not change the null space. So perform elementary row operations. So Ax equal to 0 is equivalent to by row reduction. So you get this A is equivalent to 1 0 1 2 1 0 1 1 1 2 0 0 0 0 0 0. The last two rows are zeros. So Ax equal to 0 is equivalent to this reduced matrix into x1 x2 x3 x4 x5 equal to 0. Solving this, you get x1 equal to minus r minus 2s minus t, x2 equal to minus r minus s minus 2t, x3 equal to r, x4 is equal to s, x5 equal to t. There are 5 unknowns. So, and the third and fourth rows are zeros. So you can choose x3, x4 and x5 as free variables. Okay, so we have expressed them or in the vector form. So the corresponding vectors v1 equal to minus 1 minus 1 1 0 0, v2 equal to minus 2 minus 1 0 1 0, minus v3 equal to minus 1 minus 2 0 0 1. They span the null space. So it is enough to prove that they are linearly independent too. So take their linear combination and you can easily see that they are linearly independent. Therefore, these three vectors form the null space of the given matrix A. Okay, again the fourth theorem says that elementary row operations do not change the row space of A. So the row space of A is equivalent to the row space of the reduced matrix. Okay, therefore, and the last two rows are zeros, which means the row space of A is spanned by the row vectors R1 and R2, first and second rows, because these are the linear combinations of all the rows of the vector, of the matrix, but zero vectors or zero rows does not affect the linear combinations. Therefore, they are spanned by the first two rows 1 0 1 2 1 and 0 1 1 1 2. Okay, and also you can see that these two vectors are linearly independent and they form the basis for the row space of A. Next is the basis for the row and column spaces of a matrix in row echelon form or row echelon form. Row echelon form is by row reduction we can convert the matrix into row echelon form. So we have a theorem. The following theorem helps to find basis for the row and column spaces by inspection. So here we see the row and column spaces just by inspection on the given matrix. And what we do is, of course, we reduce into row echelon form. So the theorem is, if A is a matrix, or if a matrix R is in row echelon form. So what we do is, if a given matrix is A, we reduce it to row echelon form. So if a matrix R is in row echelon form, then the row vectors with the leading ones form a basis for the row space of R. So the non-zero row vectors, because they have in row echelon form, the non-zero row vectors has leading element 1. So the theorem says that the row vectors with the leading ones form a basis for the row space, and the column vectors with the leading ones of the row vectors form a basis for the column space of R. So the basis for the column vectors of R consist of those columns whose rows has leading ones. Let us see an example. Let R equal to the 1 2 3 4 by 6 matrix 1 3 minus 2 0 2 0 0 0 1 2 0 0, all zeros, last entry 1 and the last row 0. Then this is in row echelon form. The row vectors with the leading ones are the first three rows R1, R2 and R3. Therefore, they form a basis for the row space of R. And the column vectors with the leading ones in the rows, first row has leading 1 at C1, second row has leading 1 at C3. Okay, C3 means third column. Okay, and the next leading one is in the third row at the sixth position. So A36 is C3. Okay, decides C3. So first one R1 at C1. Therefore, the first column vector is 1 0 0 0. Then the second one occurs in row 2 at third place, second row, third column. So third column is the second basis element, minus 2 1 0 0, and the next leading one occurs at sixth column. So sixth column is the third column vector basis element 0 0 1 0. So they form a basis for the column space of R. Okay, next is the basis for the column space of a matrix. We have already seen in the above theorem 5 that given a matrix, you can row reduce it to echelon form, and just by inspection we can determine the row basis or basis for the row space and basis for the column space of the given matrix. Now, basis for the column space of a matrix. We know that elementary row operations do not change the column space of a matrix. Of course, they change the do not change the column space. Okay, sorry, my mistake. Elementary row operations change the column space, of course, because there is an example. You consider A as the 2 by 2 matrix 1 2 5 10, which is equivalent to 1 2 0 0, and the column space, first one is spanned by column vectors are spanned, column space is spanned by 1 5, because 2, 10 is a linear combination of 1, 5, and the second one is spanned by 1, 0. So both are distinct, because in the corner space of B, the second row is always 0. Okay, hence they are distinct. So what I meant to say is that elementary row operations will always change the column space of the matrix. Elementary row operations change the column space of the matrix. But elementary row operations do not alter the dependence or independence relations among the column vectors. But they change, even though they change the corresponding spaces, they do not change the dependence or independence among the column vectors. In fact, if w1, w etc. are transferred to u1, u2 etc. un by elementary row operations, so this w1, w2 etc. wn are the columns, of course. So these columns are transformed to u1, u2 etc. un. Then c1 w2 w1 plus c2 w2 plus etc. plus cn wn equal to 0 if and only if for the same coefficient c1 c2 etc. cn, c1 u1 plus c2 u2 plus etc. plus cn un equal to 0. Thus elementary row operations do not change the dimension of the column space. They do not change the dimension, but the space is changed. You get another space of the same dimension. So we have another theorem, theorem 6. Let A and B be two row equivalent matrices. Then a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. And a given set of column vectors of A is a basis for the column space of A if and only if the corresponding column vectors of B is a basis for the column space of B. So very important theorem. So if the column space of A is given, then B is row equivalent to A, then the corresponding columns of A is a corresponding columns of B or A is a basis for the column space of A or B. Okay, so here in the fifth theorem, the given matrix itself is in row reduced form. Okay, so I think I mentioned A is reduced into R. So you will get only the basis for R, not the basis for A. The basis for A is obtained from the basis for R. You choose the basis for R, and the corresponding column vectors of A forms the basis for A. So I think I made a mistake by saying correspondingly you will get the basis for A. That's wrong. So here is an example. Given a matrix A, we row reduced it. So, and we have already seen that C1, C2, there are two elements, first column and second column and first column forms the column basis for the column space of R. So correspondingly the first and the second columns, say 1, 3 minus 1, 2 and 4 minus 2, 0 forms the column space for basis for the column space of A. Okay, another one is so we have obtained a basis from the columns of A itself. Okay, for the column space. Now what we do is basis for the row space from the row vectors of the matrix. So this particular theorem 6 gives the basis for A by the columns of A itself. So now see, we see how to get the basis for A, basis for the row space of A from the row vectors of A itself. So that is very simple. First we transform A into A transpose. Okay, find its transpose. Then use theorem 6. We find out the column space of A, and we not column space. We find the columns of A which forms a basis for the column space of A, and take again transpose, A transpose, whole transpose. So it is explained by a theorem. Just go through it. It's a very simple theorem. Very simple problem. Then basis for the space spanned by a set of vectors. So this is the last section, I think. We have given a set of vectors and we have to find out the basis for the space spanned by the given set of vectors. So suppose we are given a set v1, v2, etc., vn of vector or vk of vectors in Rn. So we have a set of k vectors from Rn. So we have to find out a set of vectors from S itself, which is a basis for the span of S. And also we try to express the other vectors in S which are not in the basis as a linear combination of the basis vectors. So we follow the 6-step procedure given below. Step 1 is form a matrix A whose columns are the vectors v1, v2, etc., vk. So v1, v2, etc., vk we write in column form and form the matrix A. Then find the row reduced echelon matrix R by reducing A. Then denote the column vectors of R by w1, w2, etc., wk. So w1, etc., wk are the column vectors of the reduced matrix R. Then identify the columns of R that contain the leading ones of the row vectors. Corresponding column vectors of A is a basis for a span S. Okay, so in this fourth step, we identify the row columns of R which contains the leading ones of the row vectors, and corresponding columns of A is a basis for the span of S. Then to obtain a set of dependency equation for the column vectors w1, w2, etc., wk of R by successively expressing each wi that does not contain a leading one of R as a linear combination of the predecessors that do. So what we do is we express those columns of R which do not contain the leading ones as a linear combination of the predecessing or those columns which are just or having a smaller subscript. Okay, say for example, if ws does not contain the leading ones in the rows, leading one of the rows, then this ws is expressed as a linear combination of the other basis vectors from w1 to ws minus 1. So this is clear from the given example below. And finally, in each dependency equation obtained in step 5, replace wi by vi. Okay, so it is illustrated by an example. Find a subset of the vectors v1, v2, v3, v4 and v5 given of R4 which forms a basis for the subspace of R4 spanned by these 5 vectors. Also express each vector which are not in the basis as a linear combination of the basis vectors. So A is given, so v1, v2, etc., v5 are the columns, and row reduce it, you get the rows, I mean the columns of the row reduced R as w1, w2, w3, w4 and w5. Observe that the first row w1 has a non-zero, has leading 1 at column 1, w2 has leading 1 at column 2 and w4 has leading 1 at column 4. So the corresponding first, second and fourth columns of A form a basis for the subspace spanned by these vectors. Okay, so they are v1, v2 and v4 is a basis for the given for the space spanned by these given vectors. Now we need to express the remaining vectors. So v1, v2, v3 and v5 we expressed as a linear combination of v1, v2 and v4. So what we do is the columns of R which are not in the basis for the column space of R are w3 and w5. So first we write w3 and w5 as a linear combination of the remaining vectors w1, w2 and w4. So the simplest way is expressing w3 as a linear combination of w1 and w2 of lower subscripts and w5 as a linear combination of w1, w2 and w4. So expressing w3 as aw1 plus bw2, so you get 2 minus 1 0 0 transpose because it's a column vector equal to a into the column vector 1 0 0 0 plus b into 0 1 0 0. So solving it, you get a equal to 2 and b equal to -1, which means w3 is 2w1 minus w2. So correspondingly, you're replacing w with v. v3 is equal to 2v1 minus v2. And similarly, w5 expressing as linear combination of the basis elements with lower subscripts aw1 plus bw2 plus cw4. Solving a, b, c are all ones. So you get w5 equal to w1 plus w2 plus w4, and therefore v5 is equal to v1 plus v2 plus v4. Thank you.